everyone. In the previous class, we started our discussion on openings in laminated rocks. I explained you that what do we exactly mean by laminated rocks, and I explained you the concept of immediate roof and main roof. There we saw that some of the layers upon excavation, they take part in the deformation, and few other layers they remain as it is. So, accordingly we define the immediate roof and the main roof. So, today we will see that how the multiple layer roof works as far as the excavation in laminated rocks are concerned. Now, before we generalize the situation to the case of multiple beams, first we will consider the case of only two beams which have the same length and the thicknesses as T1 and T2 and the corresponding flexural rigidities as E1 I1 and E2 I2. The width of both the beams will be taken as same and represented by small b. Now, if the load on the beams is say Q per unit length of the beam, then the deflection of the two beams will be governed by the ratio of load per unit length to the flexural rigidity. Now, depending upon which beam it is, first beam or the second beam, the load on that will be its corresponding weight. So, that we can say as Q1 or Q2. Now, here is a figure with the help of which I will try to explain you that there can be the occurrence of two conditions in case of two beams. Please remember that I will always mark the lower beam as the first beam, which is represented by this number 1, and the upper beam would be given as beam number 2, and corresponding to beam 1 and 2 you will have the thickness as T1 and T2 respectively and flexural rigidity as E1 I1 and E2 I2 respectively. This will be true for both the conditions. Now, take a look here on the first portion of this figure, where we have the thickness of the lower layer, which is T1, is less than the thickness of the upper layer, which is T2. So, T1 is less than T2. Now, if T1 is less than T2 and we have assumed that the width of the beam is going to be same in both the cases, so we can say that the value of I1, the moment of inertia, is going to be less for the first beam as compared to that for the second beam. Accordingly, if I1 is less, so we can say that more or less if this is the situation that Q1 by E1 I1 is greater than Q2 by E2 I2, then in that case we can have delta 1 which will be more than delta 2. What does this mean physically? That upon the action of their own self weight, the first beam will deflect more as compared to the upper beam. So, what will happen because of that? There is going to be the development of this zone of detachment. However, what happens in the second case? We have the thickness of the lower beam, which is this beam, is more than the thickness of the upper beam, and accordingly the I1 value will also be greater than I2. Now, accordingly, if Q1 by E1 I1 is less than Q2 by E2 I2, this would result into the situation where the lower beam will deform less as compared to the upper beam. That means the displacement deflection of the lower beam, which is delta 1, is less than delta 2. So, what will happen in this case? In this case, there will not be any zone of detachment and both the beam they will deflect together. because delta 1 is less than delta 2. Once again I will repeat that, please remember I am marking first beam as the lower beam and second beam as the upper beam, and these two type of situation can occur in case if there are two layers in the roof which are participating in the displacement. So, we have the condition 1 as I explained you, where the deflection of the upper beam is less than the deflection of the lower beam. This gives rise to the development of zone of detachment, and in condition 2 your deflection of the lower beam is less than the deflection of the upper beam, and therefore what will happen in this case is that top beam will load the lower beam and lower beam in turn will support the upper beam. So, in this case the problem will reduce to the computation of the additional load. This additional load will be because of this phenomena, since delta 1 is less than delta 2. So, what will happen is that top beam will load the upper beam apart from its self weight, and the lower beam in turn will support the upper beam. So, therefore, this additional load will come into picture. Now, before I go to the analysis of these two layer beam using the theory of beams, we have to make few assumptions, such as the coefficient of friction between the two beams have to be equal to 0. Then the deflection of both the beams are going to be equal for all the values of x. So, starting from one end of the beam to the other end of the beam, at all the points or at all the location or at all values of x, the deflection of both the beams are going to be equal. Then the upper beam loads the lower beam with a uniform load per unit length of the beam. So, this means that the loading that we are considering is always the uniformly distributed load. Further, the lower beam supports the upper beam with an equal load which is also per unit length of the beam. Both the beams, they are considered to have same length and the width. So, let us try to derive now that how is going to be the expression for deflection as well as for the bending moment and the shear force. So, as for the assumption we had that the deflection of both the beams are going to be same. So, here we have delta for beam 1 will be equal to delta for beam 2. Now, we have Q1 as gamma 1 B into T1, and we have Q2 which is the self weight of the upper beam, that will be gamma 2 B into T2. They may have the different thicknesses and different unit weight, but the width is going to be same as per the assumption. Now, let us say that the additional load is delta Q. So, let the additional load be delta Q. So, in that case our delta 1 is going to be Q1 plus delta Q x square divided by 24 E1 I1 into L minus x whole square. This will be equal to delta 2 will be equal to Q2 minus delta Q x square divided by 24 E2 I2 into L minus x whole square. See, these expressions we saw in the previous class, that how we can derive these with reference to the single beam here. Now, this equation I will mark as equation number 1. So, in this case now this for the second beam, why we are taking this Q2 minus delta Q is that now the lower beam will support the other beam. So this is how we get equation 1. Now this equation 1 will hold good for all the values of x. So we have the equation 1 must hold for all the sections along length of the beams. So therefore what you will get as that Q1 plus delta Q by E1 I1 will be equal to Q2 minus delta Q upon E2 I2. Now we can solve this for delta Q. So let us see how it is done. So we have here E2 I2 Q1 plus E2 I2 into delta Q. This will be equal to E1 I1 into Q2 minus E1 I1 into delta Q. Now collect the terms for delta Q together. So I will have here as E1 I1 plus E2 I2 into delta Q. This will be equal to E1 I1 Q2 minus E2 I2 Q1. So this additional load, which is equal to delta Q, can be written as Q2 E1 I1 minus Q1 E2 I2 divided by E1 I1 plus E2 I2. So this is how we will get equation number 2, and the expression for Q in terms of weight and the flexural rigidity of the beams, lower as well as the upper beams. Now I can substitute this expression for delta Q in the earlier expression, that is equation number 1. So we can obtain the expression for the respective deflection. So here if I just substitute this, what we will get is delta 1 is equal to delta 2. That will be equal to, say I write here as Q1 plus Q2 E1 I1 minus Q1 E2 I2 divided by E1 I1 plus E2 I2 into x square upon 24 E1 I1 L minus x whole square. And therefore we can write here as, just simplify this and you will get an expression like this: x square divided by 24 E1 I1 plus E2 I2 into L minus x whole square. Make this equation as equation number 3. Or you can write delta 1 is equal to delta 2 as Q1 plus Q2 by 2 into x square divided by 24 E1 I1 plus E2 I2 by 2 into L minus x whole square. Now if you just compare this equation number 4 with the equation of a single beam, so then you will realize that these two beams are acting as one beam, except for the case that their weight we can take as the average of their individual weight, and the flexural rigidity can also be taken as the average of their individual flexural rigidity. So, this is a simple form where you can obtain the expression for the deflection of both the beams. Now, the interpretation of this equation is going to be in this particular manner, that when the upper beam loads the lower beam, then the lower beam in turn it supports the upper beam, and each beam deflect as if its load per unit length and the flexural rigidity, they were equal to the respective average load per unit length and average flexural rigidity for two beams. As I explained you that in this case this Q was taken to be Q1 plus Q2 by 2, and flexural rigidity EI was taken as E1 I1 plus E2 I2 by 2. So, it is kind of an average load per unit length of the beam and average flexural rigidity of both the beams. So, this is how this equation 4 can be interpreted. Now, if we have this Q1 as gamma 1 B T1, Q2 as gamma 2 B T2, I1 is 1 by 12 B T1 cube, and I2 be 1 by 12 B T2 cube. So, in that case, now if I just substitute all these expressions in our equation number 4, what we get as delta 1 equal to delta 2, this will be equal to gamma 1 T1 plus gamma 2 T2 divided by 2 times E1 T1 cube plus E2 T2 cube into x square L minus x whole square. This is equation number 5, or we can say that delta 1 is equal to delta 2. That is equal to maybe gamma bar divided by 2 times E T square bar into x square L minus x whole square. Now, what does this mean? I have this gamma bar as the average unit weight of two beams, or I can write it as gamma 1 T1 plus gamma 2 T2 upon T1 plus T2. And E T square bar is equal to T1 E1 T1 square plus T2 E2 T2 square divided by T1 plus T2. So, basically this is weighted average value of E T square for both the beams. So, basically it is equivalent to replacing the two beams by a single beam whose unit weight will be gamma bar, and for which the value of Et square will be equal to Et square bar. So, that is how you can have the two beams replaced by a single beam, and therefore, in this case you will have delta max that is equal to gamma bar L to the power 4 upon 32 E T square bar and this is going to be at x equal to L by 2, that means at the middle point. And once you know this delta max, subsequently you can obtain the bending moment as well as the shear force at any location x in the beam all along its length. Now the equation for the deflection, bending moment and shear force for a single beam can also be used for the case of two beams which are resting on each other. See, there is no separation between the two beams. What you need to do is that you have to consider the average quantities of the two beams in place of Q and EI. Then the expression for maxima values, which is delta maximum, sigma maximum and tau maximum for the maximum deflection, normal and the shear stress for a single beam. It can be used for the case of two beams as if you are taking the weighted average of the quantities which are represented by gamma bar and Et square bar in place of gamma and Et square. So, whatever was the expression for the single beam in terms of gamma and Et square, in case of the two beams, you just replace gamma by gamma bar and Et square by Et square bar. And in that case, we can simplify the analysis by considering these two beams as an equivalent single beam. So, in case if we have n number of layers in the immediate roof, then we can have let us say the number of beams, they are say n. So, in that case we can write this gamma bar as summation I varying from 1 to n gamma I Ti divided by summation I from 1 to n Ti. I will mark this as equation number 9, and then we have Et square bar. This will be equal to summation I 1 to n Ti Ei Ti square divided by summation I varying from 1 to n to Ti. So, this is how we can handle any number of beams which are participating in the deformation, and we can find out the weighted average expression for gamma bar and Et square. So, accordingly, as per the assumptions, the only deflections at any section x, they are same for all the beams, but normal and the shear force for each beam will depend upon the thickness of that beam. So, we cannot say that the maximum normal and the shear stress at any section x will be same for all the beams. All we have assumed is that only the deflections are going to be same and not the maximum normal and the shear stresses. So, this is how we can handle the situation having multiple layers in the roof which represent the analysis of excavation in laminated rocks. So, till now what we saw is that we were using the theory of beams to analyze the excavation in laminated rocks. But in the previous class I explained you that depending upon the aspect ratio of the opening, you have to either apply the theory of beams or theory of plates for the analysis. Now, in case if the situation is like that the bending in the roof is happening both ways, that is not only in one direction but in both the direction, then in that case one has to use the theory of plates. How this is done, what all are the various conditions, all these things we will learn in the next class. Thank you very much.